This section we deal with homology. We deal with homology before, now we deal with homology. We construct here quickly the homology of a discrete group. Still discrete group, the situation is due to the situation of cohomology. A be G module, let dA be the subgroup generated by the element of A acting by G, then minus A. So you see that as you quotient by this ideal is quotient by this submodule, then it's invariant under stable. It's invariant under the action of G. The quotient is denoted by AG. It is the largest quotient of A, where G acts trivially. If there exists quotient map of G modules, where the G action over B is trivial, then it factorizes the ray G. Similarly, the fixing point of A is the largest subgroup where the action is trivial. And AG is the largest quotient of A where G acts trivial. The largest quotient. Where G acts trivial. This is the largest subgroup where the action is trivial. Well, at the beginning it may feel a little strange, confusing with these two modules. What's the relation between these two? One is the largest quotient, that's Gx trivially. One is the largest subgroup, the action Gx trivially. Well, it's not that stupid, not that strange. Say, what does it? Telling you start with G module A. We want to see if there is any connection between the two. If you have morphism from A to AG, then by the definition, by the property of this quotient, it tells you if Gx trivially has a module through a morphism of G module, then this factorize. Do we have something here? Yes, we have the norm. Okay. What's the relation between these two? Well, are we comparing which is bigger? Actually, no. We're just saying that as a subgroup, This is the biggest one that Gx trivial. On the other hand, G has action A, has action AG, and G also has action on quotient of A. But here the action may not be trivial, but here the action is trivial. I'm asking, under what condition is this action also trivial? Obviously, we are not connecting these two submodules, I call this submodule, but this is not submodule, it's quotient module. Well, what is the biggest quotient? This is the biggest quotient, but this is just A. It's not trivial, so to become a trivial G module, at least they have to kill all elements of this form. Okay, that's our DA. That's why I say the biggest quotient is a trivial one. There's no obvious connection, although yes, it's definition there must be homomorphism between them. Remark that the quotient to the biggest quotient, the functor to turn it into the biggest quotient of trivial quotient module is a functor into the category of groups, given morphism of G modules, thereby the universal property of AG. We have a well-defined morphism from AG to BG. The functor G is right exact. Okay, we got the right exact functor. What's the good of it? By the problem, we construct a left-derived functor of. For right exact functor, we construct a left-derived functor. For left exact functor, like home functor or fixing point functor, we derive the right derived functor. Actually, yes, as I just said, recall that the fixing point functor is a left exact. And this functor is a right exact. This functor we consider the right derived functor. Which is HI. Okay, here we write index in the lower position. We remark that we have to consider projective resolution. While in this case, if we put a module here, we consider its injective resolution. Wow. Now we have to consider projective resolution. Everything is due to each other. We recall that if G is not discrete G module, if G is not discrete, there is no enough projective. We also remark that this functor is equal to this functor, Z tensor with ZG. Well, to have a little feeling, surely if you want to. See clearly, you have to construct isomorphism. Right? For example, if I send in A to, how about just 1 tensor A? In this, actually we write like this. So this well-defined, we have to say whether this well-defined means that to be well-defined, you have to say that one tensor is so equation dA is equation by the submodule generated like this. So take up energy submitting group, so the quotient of what is the operation is given by the summation. So what is this? Let's see, 1 tensor A plus 1 tensor G dot B minus, all we have to prove is this equals 0. Okay, is this 0? So the action of ZG on the right hand side, how do I move it? How move this action on the left hand side? And we have to know how is the left hand side. Be there and the ZG mode. How is it be there and ZG mode? It's by the trivial action. It's by the trivial action. Also here he didn't write it clearly. Surely by the trivial action. So you move it left. It's just G till 1. It's just the 1 itself. So you see it's well defined. It doesn't depend on the choice of the element. Of course, to see this is isomorphic, you still need to see its trajective and injective. Okay, if you want, we can do this. Try to do. Let's see. Do we describe it more clearly? Just for fun. We don't do this very often. Just feeling that it's clear. Sometimes our feeling is not solid. So we want to make it better. So this is group homomorphism. We have to check its group homomorphism, actually isomorphism. So define it this way. It's well defined now. What we have to check first is group homomorphism. So A plus B should be which means that 1 tensor A plus B should equal 1 tensor A plus 1 tensor B. This is okay. Second thing we check is 0 to 0. Okay, it's 0. The third thing is checking the curve as a group. Okay. Those elements such that okay. But 1 tensor A equals 0 implies what? We claim A is 0. How do we prove this? To show an element of a tensor product is 0. It's not that obvious. You have to use the universal property. Since by the universal property, let's recall elementary tensor, elementary element of a tensor product, say x tensor y equals 0 if and only if x is in the module R module E and y is in R module F. So it's in this tensor product. It's equivalent that for every R bilinear map, the image of this element is 0. Why this is so? Let's recall by definition. Best definition of tensor product. It is the ring, it is the module such that this homomorphism sending x y to x tensor y factorize for any bilinear homomorphism. So at this moment, if x tensor y is 0, then surely since this is a group homomorphism, it must be mapping to 0 for any bilinear homomorphism. But conversely, if the wrong direction. But conversely, if you have 0 for any bilinear homomorphism, itself must be true. Okay, suppose x tensor y is not 0. We can construct a bilinear map such that this is not 0. Yes, we can. We construct one. Okay, this is bilinear homomorphism. Which is contradiction. Okay, actually you see my argument, but I don't have to be so troublesome. I don't have to dirty my hands. If for any bilinear map this is 0, then particularly for this bilinear map it is 0. That's it. Okay. So about our situation, we have to use this description to show that one tensor is 0. If and if A is 0 itself, in this situation, can we construct? If it's not 0, can we construct a bilinear homomorphism such that this is not 0? How about this one? How about this one? Of course, you have to do this and ZG mode homomorphism. Is this bilinear? If you do why this is just a 1 plus, which equals, so you see this is the same as okay. This is firstly, this is on this position. It's when you fix any point, fixing any element here, then from this position to the ring A through this map, this is a ZG linear homomorphism. Okay, so we first check its homomorphism. So you have to check its ZG linear, which means that for any element of ZG, you're acting on an element here. It should be the same as then you acting the well, here is just since the action is trivial, the action of G is trivial in this group. This one is mapped to yes. Surely I'm writing something very stupid. I'm really sorry. You're not able to directly construct morphism from the tensor product to some ring. You do not know if it exists or not. Okay, if you say you can, I believe you, but I mean you must start from the product. And to show this is bilinear, then there exists naturally isomorphism from extensor from the tensor A to A. And I didn't notice, but surely here I should write like this. Then let's rewrite. To be honest, I'm very optimistic about this map. Maybe it works for this one. Let's first try this and see whether you can find a bijective map. if we simply do like this as ZG modi, is it bilinear as the morphism ZG modi? So just how it is equal. For fixing y, we'll call this phi y, this position. This tells you phi y x1 plus x2 equals phi y x1 plus phi y x2. So homomorphism in the first position. So we check whether it's ZG linear. So we have to check phi y for any element from ZG. This is element of ZG acting on Z, then acting on Y as Z module. This is element of Z acting on Y, then on A. Sorry, what I said. First, this element is first X acting on Y, yes, element of A, then X acting on it. I'm doubting this is not true. You easily see, take an element G from G. G has element of ZG when you're acting on some element N of Z. Acting on Y, because it's trivial here, it's just N acting on Y. But here what you do is G acting on what? Acting on N acting on Y. This is G module. G respect the additive operation of A. This is okay, that doesn't matter. I don't have to write like this. I mean, one is just G acting on NY, one is just NY. So maybe it's not equal. So you see, we do need to working on the fixing element of A. You see? Okay, we don't have to work on this, but how about the fixing point of A? To this, I think is okay. If we do this, we already see this works. So it's a ZG linear on the first position. How about the second position? On the second position, it's consider phi y, phi x, fixing x, and consider on the second position. So phi x, y1 plus y2. So obviously, phi x, y1 plus phi x, y2. Is it linear? Element K acting on y. Is it equal to phi x acting on y is acting linear? This is x acting on psi acting on y. As the G linear. This is psi acting on x acting on y. Are they the same? Since x is just element of z as z module. Here is, for example, it's n. If it's just like n summation n times y, because I is from G. If psi is from G, then it commutes by the definition of a G module. It commutes with the operation of adaptation. But if psi is not only from G but from ZG, how is it? So for example, if psi is the IGI, we acting on it, it should be just like this, right? And if you're using this to acting on n, what is it? It should be, as we said, it's component acting on it. For this trivial on n, it's just an I acting on n, and take the summation. So this one, it looks like they give different thing, but when you're acting on element of y, it's the same, because G is a trivial on y. Just left with the multiplication of integer should be the same. So we do construct a bilinear map as modules from Z product A to AG. Hence, I'm using this to check what? To check one tensor A must be 0 implies A is 0. If it's not 0, we see that we construct some bilinear map is not mapped to 0. How about this one? Is this really working? So it's coming from here with A not 0. By our construction, they should be mapped to this should be mapped to acting on A. So here's A. So it's not 0. You see, it's not 0. But we exist morphism like this. This is not 0. It means this is not 0, because this is 0, then it must be 0. So we prove it. Okay. Is there any problem with this? I don't think so. construct the bilinear homomorphism of the G module, mapping this element to a non-zero element. So it means this one must be non-zero. And we saw one tensor A for any non-zero is non-zero. I think it's nice, although it's stupid, but it's nice. So there is a little computation. We did a little computation here, and we show this is yes. So yes, we show this kernel. First, I think I already said this is well defined. We checked it because you add the element from the kernel. Then this is the same because one tensor G is 0. Okay, and then I checked this homomorphism between 0 to 0, and the kernel is 0, so it's injective. So finally, is it surjective? This is happening category. What is injective and surjective? It's isomorph. So is it surjective? So any element from the right hand side, what should it look like? It should look like this summation. With the generator, since this is a homomorphism, we only have to look at the generator. So we just look at the element like that. And tensor is A. Yes, an element is mapping to this. And we say this is just one tensor. So this one is okay. Well, the problem is no, there is no problem. I was thinking, okay, do I have to check this element is really in this quotient ring? But no, I don't have to check because this is the equivalence class. So the only problem is, okay, I have to check whether this is well defined, but this is what I checked at the beginning. This is representative of this equivalence class. Any element in the same class must be mapped to the same thing. Already checked. So okay, we checked. Indeed, is isomorphism and ZG module. Okay. So back here, we show this is equal. So we have that the left derived functor are equal. In the second case, it is called torsion. Just as in the case of Exter, one can prove that one obtains the same derived functor if one considers the first variable, the second one. So one way to compute the homology is to use the standard project. the resolution of Z and apply tensor product. So finally, we get the following thing: element of this module can be identified with functions from Gn to A, which is 0 for almost all the points of Gn. In the tensor product, Bn is considered as a right G module and action is given by. We remark that C0 G is A, the boundary is given by. Surely, as it wrote the standard projective resolution of Z, so it's the same Pn as before. We write lower index. So you just write the projective resolution of Z, then you apply the tensor product and compute the nth position cohomology together. Cohomology group for this. This is just telling you how it looks like. That is claimed as it claimed, this can be identified with functions from Gn to A. This is 0 for almost all the points of Gn. This is something new. Honestly speaking, I don't know how he got this identification. But anyway, this doesn't matter at this moment. When we come back, when we have more time, we just continue to see how to compute this homology. I did know the kernel of the map, which sends this formal summation, just the summation of the elements of Z. This group is generated by G minus 1. Remark that. It's not surprising this is generated by G minus 1. We remark that for any G module A, we have this. So you see, if this is generated by G minus 1, then this is really, by definition, a G scaling the element G, acting on some element, the minus it. Okay? So now let us consider the sequence. By the definition, got the exact sequence. We have that. Yes. Because H0 is just the functor acting on the element. The functor is quotient by Ig. So acting on Ig is Ig quotient by Ig. Square acting on is quotient by Ig. So H0 G2. Ig is trivial. Okay, this one is trivial. So since we are dealing with homology, what is your long exact sequence? Pointing, what is the direction of a long exact sequence? Well, I'm a little confused about what he write here, because here he writes something not correct. Surely I agree, since you are in the discrete case, you're just considering the left derived factor of the factor of the tensor. So if you put the projective object here, the G module projective, the G module here, for example, you put ZG here, and consider this. This is a projective DG module, so tensor product with a projective. It's in particular tensor product with a flat ZG module, so this is exact. So all the cohomology group should vanish, but except 0. Except 0, because when we define H0, using the kernel quotient by the image. H0 is just the kernel of D0. After that, since your exact functor is sending this exact sequence to exact sequence, all the other homology group are just kernel quotient image. They all vanish, but except H0, because H0, as we know, it should be just this functor acting on this module. See, in our case, this is just the tensor with the G and the G module should be Z. As we saw, also here it should be A quotient by IG, A in this case the G quotient by IG. And you can check this is indeed the G module homomorphism. So the G quotient by IG and the G module should isomorph to Z. This is whatever case. If this is the case, our problem is we want to compute this, I guess. We want to compute this, so what we do, we compute with long exact sequence in the homological cases. It is like so H1 G IG H1 G 3G, this is 0. H1 GZ right here, then H0 GIG, which is isomorphic to IG, which is IG squared, then H0 G ZG, so isomorphic to Z, so H0 GZ just Z quotient by IG IGZ. But GX trivially on Z, so Z quotient by IGZ is Z quotient by Z, it should be 0. So this one should not be isomorphic to this, I think, because if you are isomorphic to this one should be 0, but it's not. So there's some problem with this. So you put doubt here. Okay. As for homology, we still have functionality with respect to group G if we have a morphism. We remark that a G is a quotient of the A regarded as module of G prime. So we have morphism, functionality, factorial in A, which can be extended to morphism for any Hn. So kind of factorial in G. Maybe G module and a prime or G prime module, let's not suppose that they have morphism of within groups compatible with F. Yes. So we have morphism like this, composing with right morphisms. If we set F by inclusion, in the homology case we have this, which is not normal subgroup. We have this here. I think he writes something in this. We have the following exact sequence, as we proved in the case of homology. Dimension 0, we define this, so it extends to a morphism cohomological factor. It's exactly the same thing we did with cohomology. If the cardinalities and we have this, completely this. This is in the H0 level. This restriction, co-restriction, doesn't depend on the Q. I mean, it's defined for any index Q. So when we say this, actually we mean this works for any cohomological group or any homotopy group. That's what we mean. Still the same, we have to show that multiplication by n is a morphism of complex which extends n, and by the uniqueness it is the extension to give it is by the uniqueness it is the one that gives you the right morphism between the homological factors. Sorry, surely I made some mistake. So where this mistake starting, let's think about it. What mistake did I made? I made a mistake when I'm trying to see the similarity, when I'm comparing the similarity between cohomology and cohomology. You see, for cohomology case, you have your starting object is A. You want to compute this. What do? You first choose the injective resolution. You apply your left exact function. This is exact. Apply your left exact function. You call this D0, D1. And you do this. The chain is kernel dn with image quotient by image dn plus 1. Sorry, a minus 1, surely. And for specially we have h0 is just kernel d0. I think we just defined it like this, which you can see is just a major FA, but FA is injective, which is isomorphic to FA. This is our case for cohomology. But for homology, what happened? You start from object A, you want to compute the left derived function of a right exact function. So you start with a projective resolution A. You apply your right exact function. you call this D1, call this D0. In this case, you see it's a little different, and you define your I to be kernel di quotient image dm I plus 1. So h0 at this time it should be kernel d0 quotient by image d1. So it too has meaning, and if you are dealing with for example, if you're dealing with the exact functor, if your functor making you exact, for example, if you're dealing with tensor product, but you tensor product with some flat algebra, tensor is some flat, this is an exact functor. This will tell you this exact sequence, and compute h0 should be vanishing. That's why we say because this is flat and the G module is projective, because so there's no priori h0 is just fa. We don't have this in the homology case. So back into our condition. I think we should have 0, as the professor said. So now there are some questions. The first one is, if this is 0, how do you compute this and this? How do you compute? Once you got this, okay, I agree, you got this. But how do you compute this if it's not just simply fa? If you have to compute it carefully, what is it? What indeed is it? So for a, it should be z you have to compute it. You have to compute kernel d0 by kernel d1. So in particular, I don't think you can just conclude like this without any condition on a, because as we already saw that this one is 0. How can you conclude like this? If you compute zg quotient by ig, it's isomorphic to this, so I don't think this is true. Okay, anyway, I believe this is true because I checked it. This is a general result. How did you get this? If you're ig, if you're ig, this is interesting because they have the G modules. So this should be 0. In this case, it should be kernel of d0 is the whole. Image of d1. Is it isomorphic to just as what we saw like this? Actually, I don't know. So I write down explicitly what is d1. This divine defined on the projective resolution Z. Recall that our PI free abelian group generated by elements by all the elements of the form with GI or in G. With all the elements of the components in G. Okay. So this gives us information that this quotient is isomorphic to Ig quotient by G squared. This tells us this tells us maybe, but I can't say this right now, so I'm not concluding here on this. But as I said, this is a true fact because I cannot prove it right now. So at least we know this fact. Okay. And there is one more thing to mention. The last thing is that is about the inflation and co-restriction. Tells you that our final result is that this is not only for 0, this is for you see. This is the result. For each 0 we see clearly what we mean. Well, here you see I'm unhappy with this again. So surely, are you sure each 0 is just a G? Are you sure? Well, let me just recall for the cohomological case, which we know and we know we're talking about. And still, really in the last section, I didn't see this clearly at the beginning. So, in the cohomological case, this is just the fixing point. First, by restriction, I see the element A to a inside, so then fixing by h can be sending by the norm factor, which sending to this well-defined map because we're fixing by h. So we just determine by any representative of equivalence class works. And then you are starting from the fixing point of G, starts from A or N. Okay, no problem here. The problem is how you start from H0 to HI. We say that by the universal cohomological factor, once you got the map on 0 position, there exists a unique extension of this morphism to each HI. The uniqueness is said that it is unique on the morphism between HI. I mean, you can get different extension, but when you compute HI, they are the same. I mean, you can give let's be more clear. You have injective resolution. Yes, and you consider the multiplication by n morphism. Then you say, then you can have many different extensions, but it tells you no matter what the extension you give to make diagram compute HI, they are the same. The morphism connecting the HI are the same. So for instance, if we just multiply by n on each position, this makes this diagram commutes. Since it's injective resolution. I hope this is clear. Yes, because these are all abelian groups as modules, so multiplication by n doesn't change anything. You always have n acting on x, n acting on fx. There's no problem. I mean, fx, this is fx, here is x, okay, f, they are the same, so it commutes well. Okay, so then starting from this, we apply that. Then this multiplication by n will give rise to any hi, this one. It will appear to be multiplication by n, just whether you are a function or not. To send to this. Although we don't know what is co-restriction and restriction between, but we know globally. Oh, I don't say global, I'm sorry. But we know it looks like this when you compose it, because it's just function to function. And if your module are given by multiplication by n, surely looks like this. This is very nice, right? It's very subtle and concrete. Finally, I think I say something more. I'd like to say that there is much easier proof to show that what we proved. There is much more easier proof. We use the exact sequence of CG module. They do the tensor product with A. Since the tensor product is right exact, we have this is just A. So this is injection, so yes, got it. Okay, I think I stop this section here. This is it's a nice family. It's a nice family, except there are some details not very precise. I hope as I got a chance I will explain them well. I think I stop here. Thanks.